Okay, are you able to see the screen?
Not yet, sir.
Okay, wait. Okay. Now you're able to see, huh?
Yes, sir.
Okay. Okay, so last class we are looking at this example, okay? That's how we use the slack variable method to solve this particular problem. Okay. This one, okay. So basically in this method, we have to use this switching condition. Okay, that is u into s is equal to 0. So either you get, so first you have to put u equal to 0, that is inactive constraint, or s equal to 0. Okay. I think there is some delay in the laser pointer. Okay. Let me just reconnect again. Some sort of delay is there. Okay. Okay, we'll try again. So either you put u equal to 0 or s equal to 0. So u equal to 0 gives inactive constraint, and s is equal to 0 gives active. So one of these will give absurd results like s squared equal to -1. Okay, so then that can be cut off. Then the other will be correct. So this is called switching condition. That is how you check a constraint is active or inactive. Okay, so next we'll apply this same method to a little bit more complex problem. So in this problem, there is one equality constraint and one inequality constraint. So how to solve it with the slack variable approach. Okay. So So this objective function will come here, okay? And equality constraint will come here. Okay, so this is the equality constraint. And inequality constraint will come here. Okay, like this here. Okay. So you write this Lagrangian. So in this Lagrangian, this the word u represents inequality constraint and the word nu represents equality constraint. So in the inequality constraint, you have to add this s squared to make it equality constraint. Okay, so then after that you follow the usual method. Okay, so all the del of L value has to be found out. So we write down all the KKT conditions. Okay. KKT conditions are written. The first is partial L by partial S is equal to 0. Another is partial L by partial Y is equal to 0. So that is these two. Then another is partial L by partial nu1 is equal to 0. And partial L by partial u1 is equal to 0. Partial L by partial s1 is equal to 0. Okay, so this will give the switching condition. So start from here. Okay, start from the switching conditions. And then lastly, the value of u should be either 0 or negative. So why u can be negative, we'll see later. Okay, you have to start from here. So either you put u1 equal to 0 or you put s1 equal to 0. One of them will give absurd results. Okay, so first we can see. Okay, first you put u1 is equal to 0. Okay, when you put u1 equal to 0, these terms involving u1 will become 0. Okay, so if you solve this equation, okay, suppose you solve this, okay. Okay, so you get nu1 equal to -1. Okay, so if you substitute that here, you get x equal to -0.5. Okay. Then that -0.5 you can substitute here. Okay, then you will get some value for y. Okay, y may be okay. So, okay, so x star equal to -0.5, y star equal to 6.5. So this will be 6.5. Okay. There is some delay in the. Okay. So this y is 6.5. And the value of nu1 is -1. Okay, then what you do is this point x star y star satisfying the equation 4. So is it satisfying this equation 4? Okay, satisfying equation 4. So if you substitute in equation 4, you get s squared is equal to -16.5. So that is an absurd result. Okay, so that is s is equal to root of -16.5. So this is absurd result. So it means that this constraint is violated. Okay, this constraint is violated. Okay, so this u1 is equal to 0 is an absurd result. Right? So we have to try the next option, which is s1 is equal to 0. So if you put s1 is equal to 0, then the inequality constraint will become active. Okay, so the solution will lie on the boundary of the inequality constraint. So if you put S1 is equal to 0, this term will become 0. Okay, then from this 4 equations, you can find the value of x, y, then nu1 and u1. So from the 4 equations, you can find these values. So let us check what is the values. Okay, so you get x star y star is 1.5. Okay, so x star y star is 1.5, so it satisfies both the constraints. If you substitute in both the constraints, this will satisfy. And also the value of u1 is negative, which is acceptable. Okay, and the value of nu1 is 7/3. Actually, as far as the nu1 is concerned, any sign is okay, plus or minus, because the contours can come from both sides of the equality constraint. Okay, so this is the right solution. X star y star is 1.5 is the right solution. Okay, next we try to solve one simple engineering problem with this Lagrange function approach, and we run into a lot of complexity. So this example is just for illustration. Okay, nobody will do this in practice. For engineering problem, people will only use the algorithm. This hand method like Lagrange multiplier will be extremely complex. So following example of a seemingly simple engineering problem illustrates this. Okay, so simple engineering example with inequality constraint. Design of a wall bracket. The design variables are the area of cross section of bar 1 and area of cross section of bar 2. You have to minimize these areas so that the weight of the 2 bars is minimized. So okay, length of the first bar is 50 centimeters and length of second bar is 40 centimeters. So objective function is 50a1 plus 40a2. Okay, and 2 constraints are given. What are the 2 constraints? 2 constraints are in member 1, the stress, that is the axial stress, must be less than 16,000 Newton per centimeter squared, and in member 2, axial stress must also be less than 16,000 Newton per centimeter squared. So the force in member 1 is calculated as 2 into 10 raised to 6 Newton, and force in member 2 is calculated as 1.6 into 10 raised to 6 Newton. And so we can write the stress constraints. So G1 is less than or equal to 0. So stress in member 1, okay, this stress in member 1 minus 16,000, that's the allowable stress, must be less than or equal to 0. Then stress in member 2 minus 16,000 must be less than or equal to 0. So that is the constraint of the second member. Okay, so these are the 2 constraints for the stress. Okay, then 2 more constraints are added to prevent areas A1 and A2 from being negative, because you are minimizing that 50A1 plus 40A2. So if negative areas are allowed, then it will give A1 and A2 as minus infinity, because that is the lowest value possible if negative values are allowed. So to prevent that, we say that minus A1 should be less than or equal to 0, or A1 is greater than or equal to 0. Then minus A2 is less than or equal to 0, or A2 is greater than or equal to 0. So these are the constraint number G3 and G4. Okay. If we graphically draw this, we can see that it's a convex optimization problem, and it will have only one solution, A1, A2 for this. Okay, so all the other solutions will be giving absurd values. Okay, so now all these four constraints are written as slack variables like this. So you add this S1 squared here, then S2 squared here, S3 squared here, S4 squared here. So they are converted to equality constraint with the slack variables. So we write this Lagrangian equation. So this is the objective function. That is 50A1 plus 40A2 is the objective function. This is the first constraint. This is the second constraint, third constraint, fourth constraint. So you can see that this has become a very complex problem already for a manual calculation. But we are looking at it just as an exam. Okay. So this will not be asked for exam or anything like that. So we just want to see how you can solve this manually and what are the complexities involved. Okay. So everything is written like this. So now first you have to write del L is equal to 0 or partial L by partial A1 equal to 0, partial L by partial A2 equal to 0. So they will give these two equations. There is some sort of delay in the pointer. I don't know why. So you will get these two equations. Okay, then remaining values of del L is also there. That is partial L by partial U1. Okay, will give G1 plus S1 squared equal to 0. And then partial L by partial U4 will give G1 plus S4 squared is equal to 0, etc. Okay, then finally switching conditions. That is partial L by partial SI will give UISI is equal to 0. Okay. So U1 S1 is equal to 0 to U4 S4 is equal to 0. Okay. So this will give 16 different combinations of switching conditions. Okay, first combination is like U1 is equal to 0, U2 is equal to 0, okay, then U3 is equal to 0, U4 is equal to 0. Okay, and the last one is S1 is equal to 0, S2 is equal to 0, S4 is equal to, S3 is equal to 0, S4 is equal to 0. This is the last one. So in between, you will have other combination like U1 is equal to 0. That is first constraint is inactive. Second constraint is active. Third constraint is inactive. Then fourth constraint is active. Okay. So all these intermediate conditions are there. So this will give 16 combinations. Okay, 16 combinations of switching conditions. So first row is all constraints are inactive. That is U1 equal to 0, U2 equal to 0, U3 equal to 0, U4 equal to 0. last row is all constraints are active. That is S1 equal to 0, S2 equal to 0, S3 equal to 0, etc. And in the intermediate stage, you have various combinations like first constraint active, first constraint inactive, second constraint active, third constraint inactive, fourth constraint active. So 16 combinations are there, and because this is a convex problem, only one of these 16 will give the good results or the non-absurd result. All the other 15 combinations will give absurd result, like S1 squared is equal to -3, S2 squared is equal to -4, etc. So strictly speaking, you have to manually try all these 16 combinations and find which one is the which one is giving non-absurd results. So we look at some combinations. So first, let us try a combination of this one. Okay, that is all constraints are inactive. All constraints are inactive. So it is not showing my pen. Okay. So this combination, which means that all constraints is inactive, will give absurd results. Okay, so because it gives A1 and A2 equal to -infinity. Okay, because if you minimize this objective function, 50A1 plus 40A2, then if there are no constraints, then it will say A1 is -infinity and A2 is -infinity. So this will give absurd result. Okay, then second constraint is all four constraints are simultaneously active. Okay, so this is unlikely because the solution is lying at the intersection of the four constraints. So that is unlikely. So this type of things you can check last. Okay, it is not likely to work. Yeah, that is the solution will lie exactly at the intersection of four different constraints. So now we look at some other intermediate constraints. So let us try this combination. Okay, that is first constraint is active, second constraint is inactive, third constraint is inactive, fourth constraint is inactive. Okay, so then, okay, so it means U2 equal to 0 and U4 equal to 0. So let us take this equation. Okay, partial L by partial A2 equal to 0. Okay, so if U2 equal to 0 and if U4 equal to 0, then you get absurd result that 40 equal to 0. Yeah? So this condition will not work. You get absurd result 40 equal to 0. So next we'll try another combination of constraints. So let us assume that second constraint is active. Okay. Then first constraint is inactive. Third constraint is inactive. Okay, and fourth constraint is inactive. Okay, so here, okay, so let us take this equation, partial L by partial A1 equal to 0. So, okay, so U1 is equal to 0, U2 is equal to 0. Okay, so this gives the absurd result that 50 equal to 0. Okay, so one by one you have to eliminate all these 16 combinations. So finally, after a lot of trial and error, we find that the correct combination is S1 equal to 0, S2 equal to 0. S1 equal to 0, S2 equal to 0. Okay, that means the first constraint is active and second constraint is active. Fourth constraint is inactive. Okay, so let us wait for the ink to come back. Okay, it's taking some delay. Okay, so let us uh, solve this equation, and you get A1 equal to 125, A2 equal to 100. And the values of U1 and U2 are coming negative, which is acceptable. Okay, so this is how you get the correct answer. The observations, constraints, G3 and G4 are inactive. They don't affect the solution. Okay. So, and second point is, because this is a convex problem, there is only one acceptable solution out of 16 possible solutions. So then if the problem are non-convex, there may be more than one acceptable solution. In that case, we may get multiple solutions, and we have to choose the solutions which give the smallest value of the objective. Okay, so in this particular problem, so if you draw the feasible region, okay, so this is the feasible region, okay? This is G1, this is G2. So this is the axis of A1, axis of A2. So this is 0, okay? So we also gave the constraint that this A1 should be greater than or equal to 0, A2 should be greater than or equal to 0. But that is not necessary because the solution is here. So the contours of the objective function are coming like this, and it is touching here. So okay, so this is the values of A. That is 115 or 100 or something like that. Okay, I don't remember what the values is. Okay, 125 and 100. Okay, 125 and this is 100. Okay. Okay, so actually there's no need for this, no need for saying that A2 should be greater than or equal to 0, or A1 should be greater than or equal to 0. Okay, so you could have allowed the negative areas also. Okay, you could have allowed these negative areas also. Okay, and it will not affect the solution. So that is why it is saying that G3 and G4 are inactive. They are useless constraints. So even if you ignore G3 and G4, you will get the correct answer. Okay. But then some properties of Lagrange multipliers. So earlier we said that the sign of U should be negative and all. So why it is like that? So it can be shown that the value of the Lagrange multiplier, that is U star or mu star, is the rate of change of objective function with respect to unit change in constraint boundary. Okay. So, okay, let me exit and again see if this problem is going. Oh, maybe internet is slow today. Okay, that may be one reason.
Maybe, sir.
Huh? Let me just. Um, Option seems to be all right. I don't know. So the mouse itself is dragging slowly. Mouse pointer is not moving fast. Okay, shall I log out and come back again? Okay, I will log out and come back again.
Okay, sir.
Okay.
Okay. Okay, sir.
Sir, are you saying something because we are not able to listen to?
Okay, okay. I think I'll put to mute. Okay, so now you are able to hear.
Yes, sir. Yes, sir.
Okay. Okay, so we are going to see why this sign is now. Why u is negative and v can be any sign. Okay, and the meaning of Lagrange multiplier nu or u is equal to df by dh, or the rate of change of objective function with respect to unit change in the constraint boundary. So the boundary of the constraint is moved in the plus direction by 1 unit, whether the objective function will increase or decrease. So if the rate of change is positive, u is positive. That is, if the objective function value increases when there is a unit change in the constraint, then u is positive. Otherwise, you will be negative. So let us look at the explanation for negative sign of u in minimization problem. Okay, so assume this minimization problem. So these are the contour. of the objective function. Minima will occur here, and as you go away, the contour values will increase. So our goal is to reach as close as possible to this minimum. Okay, so let us define one constraint of the type gx is less than or equal to 0. So this is the feasible region. So here gx will have negative values. Okay, here gx is equal to 0, gx equal to -1, -2, -3, -4, etc. So as you go away from here, as you move the constraint boundary like this, the value of gx will become more negative. So as per the definition of the what is that of this Lagrange multiplier, the constraint boundary must be shifted by unit positive direction. Okay, so +1. Okay, so -1 is downward, +1 is like this. Okay, so it is seen that when the constraint boundary is moved in the direction of +1, the objective function value is decreased from 30 to 20. So there is a negative rate of change of the objective function for unit change in constraint boundary. So when you do minimizing an objective function, and if the constraint is defined as less than 0, then u will be negative. Okay, so u is negative in this case because the objective function value decreases from 30 to 20 for unit increase in constraint boundary. Okay, now suppose you do maximization. Maximization means the center of the contour is the maxima, and you have to reach this maxima, and the values of contours will decrease like this as you go away from the center. So your objective function is 30, 20, 10, etc. So this is the feasible region, and as you less than or equal to 0. So as you go into the feasible region, the objective function will have values like this. Okay, but we want to go in the +1 direction. So when the constraint boundary is pushed in the +1 direction, the objective function value has increased from 10 to 20. Okay. So if you do a maximization problem with this Lagrange multiplier method, the sign of u should come as positive. So this is the explanation by the sign of u should come as negative for minimization problem and y should come as positive for maximization problems. So this is just an extra explanation. Okay, this is not required for solving the problems, but you have to remember that sign change, that is the sign of u should be negative. Okay, but if it is a equality constraint, it not you don't mind whether the objective function is on the left side or the right side. Okay, because the solution will always lie on the equality constraint. Okay, so nu can be negative or nu can be positive. It doesn't matter if you deal with equality constraint. Okay. I think we can stop here. Okay, so we'll take class next Monday.
Sir, what will be the syllabus of test, sir? I'm sorry to ask this question.
Hello?